In this section, we're going to talk about binding energy. So many of you are probably familiar with Albert Einstein, or at least have heard the name before, and he contributed a lot of things to physics, but he's probably most famous for his equation that associates energy and mass together. You've likely seen E equals mc squared before. In this equation, and in many other equations that you see in physics, the constant c represents what is the speed of light, 3 times 10 to the 8th meters per second. Now, what Einstein is saying here is that anything that has mass has some amount of energy associated with it. And so we can talk about masses of objects in terms of their energy. And so we're going to use Einstein's equation to find the rest energy of a mass of 1 atomic unit. And then we're just going to write that in mega electron volts. This is not something that you'll have to do in any of your problems. I just want to show you how this equation works, because you very rarely get to see it in use. You usually just see it and have to know what it means. So if we use Einstein's equation, and we use the mass of the atom at rest, so 1.66 times 10 to the minus 27 kilograms, and we multiply times 3.0 times 10 to the 8th squared, the speed of light squared. We get an answer in joules of 1.494 times 10 to the minus 10 joules. And if we convert that to mega electron volts, 1.6 times 10 to the minus 13 joules. We'll just divide those two values, and you find that it's 933.75 mega electron volts, about. Okay, we actually did approximate here for the speed of light. It's slightly different. It's 2.99 and some stuff, which just changes the decimals just a little bit. And so your textbook, when you use this in problems, your textbook is going to use 931 mega electron volts. And this is likely the more reasonable value for you to use, because that's what your textbook uses. But I wanted to show you how this works, where this comes from. So let's talk about the idea of binding energy. If you have an average hydrogen nucleus, you essentially just have a single proton by itself. That's a hydrogen nucleus. And it has a mass of what you see here, 1.0078 atomic mass units. If you just add a neutron into the nucleus with it, you would get deuterium, right? And deuterium has a proton and a neutron has a mass of 1.0087 atomic mass units. You would then expect, if these are real tangible things that you could hold in your hands, right? If you put these two things together, that the mass of deuterium would be the sum of the proton and neutron, right? Or 2.0165 atomic mass units. Except that if you actually measure the mass of deuterium, it's not. It's 2.0141. And so what's happening is that you're losing some energy when you combine them into a larger nucleus. This is what's known as the binding energy. Okay, these objects, a proton and a neutron, aren't physical, tangible things you could hold in your hand. You can't even see them with a microscope. Just tiny little bits of energy. And when they combine together, they just lose a little bit of energy. And it's harder to take them apart. So when the nucleus is formed, a small amount of energy is given off, right? So imagine the splash that you see when you throw a rock into a lake. Right? So you throw a rock and you see a little bit of water splash up. That little bit of energy that's given off, right, kind of sticks the nucleons together a bit better. And the rock gets stuck in the lake, if you will. And it keeps them from separating back into just single protons and neutrons. It binds them together into the nucleus. If we wanted to remove something like a proton or a neutron, we have to add some energy from outside. We have to basically throw something at it to get the rock out of the water. Right? It needs a little bit more energy to break back up. And then the more energy it loses, right, the greater the binding energy, the more energy you need to break up that nucleus, the harder you have to throw something at that rock to get it out of the water. And so it's not exactly mass as you would think of in terms of what you see every day. It's mass in terms of what Einstein was talking about. Mass in terms of energy. And that little bit of energy that's lost when they combine together. So we can calculate the binding energy of a neon isotope or any isotope. And we can also find the mass if we know the binding energy. And so a neon isotope has a binding energy of 161 mega electron volts. If this was just 20 protons and neutrons, right? So 10, there are, well, let's look at it this way. Remember that the top number is the mass number. So that's the total sum of the protons and neutrons. The bottom number is the number of protons. So there are 10 protons, and so there has to be 20 minus 10, or 10 neutrons. Protons have a mass of 1.0078 atomic mass units. Neutrons, 1.0087 atomic mass units. If we multiply and then add all of this up, the total mass is 20.165 atomic mass units. So if we just had 10 protons and 10 neutrons all by themselves in a bowl or something like that, the mass would be this. But if we combine them all into the nucleus, we lose a little bit of energy. We know the energy that we lose. So we can calculate the mass that we lose. Okay? And the change in the mass is the binding energy that you're given divided by the binding energy that we calculated a minute ago per atomic mass unit. Right, so remember we had one atomic mass unit was equal to 931 mega electron volts. And so if we know the binding energy is 161 mega electron volts, if we divide by 931, the difference in the mass, 0.173 atomic mass units. We can now take and subtract 20.165, right? The mass of all of them by themselves minus the binding energy, minus the mass of all of them by themselves, minus the binding energy, minus the mass that they lose. And you get the atomic mass of neon 20, 19.992 atomic mass units. Tried to switch colors, and it did not work like I wanted it to.